Welcome to the overview of the concretization step for sub-use case 1.2-D, where we explore the parameter sampling and the step from logical scenarios to concrete scenarios that can be used for testing. The test scenario is set in a typical urban intersection environment. Conditions include a signalized traffic light, moderate traffic levels, daytime operation, dry weather, and fully functional roadside messaging infrastructure. As the automated vehicle, the EGO vehicle, approaches the intersection, it has both adaptive cruise control and GLOSA features activated. It receives real-time messages from the roadside unit. These messages convey crucial information such as the current traffic light phases, their timing, and the intersection's geometric layout. While navigating this intersection, the EGO vehicle detects a cooperative awareness message from another vehicle that is violating the red light. The task for the EGO vehicle is to respond in time by decelerating and coming to a safe stop to avoid a collision. This scenario provides a rich testing ground for evaluating the decision-making and reaction capabilities of the automated driving system. To systematically evaluate and improve this scenario, we use an iterative optimization process. It begins with an initial sampling stage, where we obtain the parameters that influence the scenario and the value ranges within which they can vary from logical scenarios provided by the Sunrise Data Framework or expert knowledge. Along with these, we specify how many initial samples to generate for the first simulation iteration. The samples are then fed into the Sunrise Simulation Framework. Here, each sample represents a unique test case that is simulated to observe outcomes such as a collision or a successful avoidance. These outcomes are then recorded and passed to the Bayesian optimization engine. Bayesian optimization takes the results of all past simulations, including those from the current iteration, and uses them to train a Gaussian process model. This model not only predicts the outcomes of future test cases, but also estimates the confidence in its predictions across the parameter space. The optimizer uses these confidence levels to determine the most informative areas to sample next. The optimization process continues iteratively. After each round, the system checks whether the confidence levels across the parameter space are improving. If a significant portion of the space shows little to no change in confidence, indicating that the model has converged, the process stops. Otherwise, it proceeds with new samples informed by the optimizer. To create a robust set of initial samples, we use Latin hypercube sampling rather than traditional random sampling. This method ensures a well-distributed set of near-random samples that cover the parameter space more effectively. During this phase, we can also define specific constraints, for example, ensuring that the target vehicle's initial speed remains lower than that of the EGO vehicle. As the optimization advances, the Bayesian optimizer refines its training based on every new simulation result. The Gaussian process evolves, learning more about the boundaries between success and failure. This evolving model helps the optimizer generate new samples in regions where the current understanding is weakest, thereby maximizing the value of each new simulation run. To illustrate the power of this approach, imagine a simplified two-dimensional parameter space representing a cut-in scenario. Within this space, we see regions where the system consistently fails, resulting in crashes, and regions where it succeeds. At the beginning, the boundaries between these regions are vague and uncertain. However, with each simulation and update, the surrogate model becomes sharper. The uncertainty around the decision boundary is gradually reduced. Still, this improvement comes with diminishing returns. Each iteration provides slightly less additional information than the one before. Ultimately, this method allows us to focus our efforts on the most critical and uncertain areas of the system's behavior. By refining the model and simulation data over time, we gain deeper insights and greater confidence in the system's ability to safely handle complex urban scenarios like this one. This concludes the overview of the concretization for sub-use case 1.2-D.